Hi, I'm Jacob Holtom. I developed WISCANet along with a lot of other people at ASU. It's a software-defined radio network that we use with GNURadio, Python, and MATLAB to develop distributed systems and demonstrate comms and radar applications kind of simply and quickly. I'm in the WISCA lab there. So the basic concept behind WISCANet is we take a bunch of distributed RF front ends and control them with a bunch of edge nodes to do some edge compute style stuff. We have a single control node that commands them all, and we define applications for each node, and each node kind of acts independently, but they all end up synchronized to a single time source. In our case, we use GPS, but I'm investigating kind of other alternatives to reduce reliance on that and make it easier to work with and remove that requirement. But you deploy a unique application in GNURadio, Python, or MATLAB. There's no requirement that each of them run the same thing. So we kind of mix and match, kind of do cross-application compatibility and mess with one algorithm in MATLAB, but take a GNURadio flow graph and run them at the same time and kind of make them talk. And so you can mix and match your usurps and mix and match your computing environments. So we take Raspberry Pis, we run it embedded on N300s, and just kind of have a real variety of stuff going on. And you can just go ahead and download it from GitHub under the WISCA repositories for use in your own project. So the general model is, if we stop trying to do real time and instead take chunks of on-the-air time and then spend some time on processing, feedback, and whatever else we want, we can not have to optimize for real time in our development, which is what every academic wants to do, is not spend 6 months building an FPGA image and then they missed a conjugation in their algorithm and it takes forever to fix it for some stupid reason. So instead, we write it in Python, MATLAB, GNURadio. We grab people's flow graphs and swap out the sources and sinks and run them on the air. And then we mix in some MATLAB and Python. But so we have our on the air real time where we just have frames chunked up. Instead, we take frames, processing, pause, another frame, pause for some processing, and then come back. And it's a fairly general interface to work with it. And so everything transmits and receives on some timestamp, throws the samples over the wall, and then it timestamps its next operation, whether a receive or a transmit, and gets it back from the baseband controller. And so in particular in GNURadio, this flow graph probably looks super familiar to anyone who's done just a BPSK or FSK receiver. Except I've swapped out the synchronizer and equalizer with a really, really inefficient version in Python, just to kind of demonstrate that you can do this and take advantage of maybe something that's more close to the mathematical definition of an algorithm, and then dump it into your code, demonstrate it works, and then later figure out the optimizations to do it right from a computational perspective. But then the rest of this looks super familiar with the header payload, demux, and then the constellation decoder, the repacking and dumping out your data. And so the general idea instead is we initialize the radio, start up some experiments, and then we decide whether we'll receive or transmit on a given cycle for some n cycles. And so all those parameters get defined in a little WISCAnet source or sync block. And so in this case, we also take a start time in as a parameter at the top of the flow graph. So we pick a number of cycles, pick a number of time samples between the cycles. Cool. And it'll just keep going for that time, and then it'll exit. And then there's also a little synchronizer and equalizer. And so in our lab, we have just a stack of X310s that do this for some phase coherent and MIMO experiments. And we have a bunch of NUCs paired with some B200s to do some simpler, more dense radio experiments. And then we've also done some experiments where we utilize the RF NOC blocks on the FPGA and an N300 to embed our own IP cores into this processing framework. So we can test it against the MATLAB reference on one node, and then test it against our FPGA IP core built with the RF NOC framework on the N300 and see how they compare and do some OTA validation in the lab. We developed another version of this where you just, instead of having individual edge nodes, you just toss each edge node in a little Docker or Podman container, and then you can run them all on your host, kind of contingent upon how much bandwidth you can get into a single computer. So how many USB buses or how many 10 gig cards can you slap in it? But it works for slow sample rates and easy demos that you can stack on a desk. There's a small graphical interface you can wire together different applications to different nodes and then just write it out and deploy it in kind of a one-click deal. I'm flying through as I know I'm keeping everyone from dinner. But so this one should also appear super familiar in structure, as it's just your BPSK demo flow graph from GNURadio.org, just swapped out with our little WISCAnet sync at the end here instead of a UHD sync or a SOAPy sync. And it has the same parameters where we get our start time from the command line and have some delay between sample sets and some other parameters. But otherwise, it looks basically the same. And then we already looked at the RX one quickly. So now I'm going to see if this works, and I'll hop over to our demo in the lab and go ahead and show you what it looks like. So on the left side of the screen, you've got your little controller. On the right side, we've got a transmitter and a receiver node. And so I'll go ahead and just download some software to each of them and see our experiment configurations. So we're just running in a little ISM band with some B200s, and then I'll go ahead and start the execution. And so we take a startup period where we synchronize everything to the GPS constellation and make sure we're locked up and kind of ready to go. And most of the time we pause for about 20 seconds, sometimes longer if we have a huge network. And it takes some time for them all to acquire and get their clocks synced in. And then we'll just launch off GNURadio. So it starts GNURadio from the command line. What you do is you just press generate, get your .py, and toss it in a folder for deployment, and it heads out. So they're both going to go ahead and transmit at this timestamp on the screen, and it'll receive it, and then it'll do this a few more times, and eventually some messages will start popping out. So at the very bottom there, you can see it's got a little hello world message coming over here through this super inefficient implementation of an algorithm that you might find in a textbook. But now we're doing it on the air in GNURadio, synchronized between a bunch of different radios at once. So this is a version where we add MATLAB into the mix. So instead of doing it with just GNURadio instances, we can have MATLAB added here on the right. You can see the obnoxious MATLAB startup in the header, and our license is out of date. But you get the same message coming through in MATLAB and in GNURadio on the left there. They both demodulate at the same time with the same algorithm, and there's no requirement that we figure out how to optimize MATLAB to run at real time anymore. We can write our inefficient algorithms in there and take them on the air with our much more efficient GNURadio implementations. So we've goofed off a lot and made some cool things. But so instead of having to do feedback through some other channel, we just stick files on a share, and in that processing time, they pick them up and they can sense the environment and make a decision. So, one node transmits a message, someone starts jamming it, SNR drops, and then it recovers by switching some modulations and coders, just testing that feedback approach. And then we also expanded it to 5 nodes where we have 3 of them doing their own thing in band, and then the other 2 spend some time listening and negotiating and computing an open frequency, time and frequency slot, and then eventually they go ahead and insert their communications waveform in there on this thing they've negotiated over a back channel. And so basically, we can use this as a tool to develop stuff where we don't have to think so much about real-time optimization of an algorithm that searches for this optimal time frequency slot yet. We can just prove one out that it works and take care of the optimization later. And one more enabled by some phase coherence from the EDIS usurps is we can do distributed mesh beamforming on this platform, where we take a signal from a single transmitter to n distributed RF front ends, and then have them do some transmit beamforming to a final receiver. And so the algorithm that we've worked out is the optimal MMSE solution in space and time. It turns out to get enough taps in there, you end up with a fairly hefty matrix inversion, kind of on the order of several hundred or larger. And so this is prohibitive to develop a fast accelerator to do this quickly. So instead, we wanted to prove it out on the air anyways and see if there was a constraint or something, at least see it on the air before we take the time to write this beamformer optimally in an FPGA or another ASIC perhaps. And so we take it in MATLAB, invert that 200 by 200 matrix, however long it takes, and then take it back on the air the next cycle and demonstrate that we can realize this, this n squared gain over the air, or n squared m in the case of the dual mesh problem. And at the same time, we can realize some interference rejection. Since we receive an interferer at that mesh, we can also reject it with that beamformer when it combines at that final receiver. And so ultimately, there's plenty of things I still want to do, and we still want to do to improve the project, but it started as MATLAB only, and it turns out this is really limiting when you try and scale up your license or when you try and scale up your speed. But so we generalized the interface to GNURadio and Python, and in GNURadio, I hope to take some more advantage of the PDU improvements to time the packets a little bit better to and from things, and also enable some other radio front ends to be used to reduce our dependence on the usurp family. There's still some user experience improvements, considering it's just all TUI, and then some better packaging and deployment approaches to get it over a larger network quicker. I think that's just about it. Thank you for your time.
Does anyone have any questions?
So in that process where you originally had things as MATLAB only, did you have various people from your team porting things into GNURadio from MATLAB? And if so, like, what was that process like?
Yeah, so I've done it. So tomorrow there'll be a presentation doing some joint radar communication stuff. And so it's an algorithm originally written in MATLAB, and it's about a 10-line equation. But gratefully, with NumPy and SciPy, you can just map most of that directly over. And so we copy and pasted some of that code, converted it to NumPy, SciPy, dropped it into a message passing block, and dropped it straight into GNURadio. And so now it runs in GNURadio instead on this framework. So it's actually not that hard of a lift to move out of MATLAB and into Python anymore. And especially with the GNURadio tooling, I can throw together these communications flow graphs to support those techniques, provide that comms receiver and transmitter out of that box. So not a hard lift at all.
Any other questions? Well, thank you very much.
Thank you.